If we study the mechanisms of combustion and the processes by which the Earth's atmosphere is renewed, we may be able to intelligently predict the consequences of our present activities. In the laboratory, we can control the products of combustion and rescue its victims. Outside the laboratory, we have less control. Let's begin our investigation of atmospheric pollution by considering what happens to the products of combustion from a meteorological point of view. When we empty the bag, we disperse the polluted air throughout the room. The concentration of harmful gases and particles becomes low enough to live with. If we open the window, the room air and the outside air will mix. We have lowered the concentration of pollutants considerably. Outside, our San Francisco air mixes with the air moving in from the west, and we pass some of our pollutants eastward to Salt Lake City, Chicago, New York, London, Hungary, Hong Kong, Hawaii. And hopefully we close the window before the mixture gets back to us. Although the concentration is now much lower, many of the pollutants that would have killed the mouse are still in the air. Let's continue our investigation of atmospheric pollution from a chemical point of view. If we could analyze the contents of this bag of clean air, we would find that 78% of the air is made up of an essentially inert gas, nitrogen. It also contains 21% oxygen. This gas is vital to all living things. It takes part in the chemical reactions of our body, enabling us to live and work. The remaining 1% contains very small amounts of carbon dioxide, methane, sulfur dioxide, nitrous oxide, and hydrogen, along with the inert gases. Our sample of air also contains water vapor. The amount will vary depending upon the time and place the sample was collected. And we would probably find many very small dust particles and salt crystals. If we separate and measure the contents of our exhaust bag, we find 78% nitrogen, 6.5% oxygen, 14% carbon dioxide, 1% carbon monoxide, less than 1% of methane, sulfur dioxide, nitrous oxide, hydrogen, and the inert gases, and we now have a considerable quantity of suspended and settled materials. If we compare the polluted air with our clean air, we begin to see how the burning of fuels can affect our atmosphere. The nitrogen has remained the same. The gases, methane, sulfur dioxide, nitrous oxide, hydrogen, and the inert gases are still less than 1%, but the temperature is now higher. The amount of suspended material has increased, and we now have a new gas present, carbon monoxide. Carbon monoxide is the result of incomplete combustion of carbon fuels. When we breathe carbon monoxide into our lungs, it combines with our red blood cells in preference to oxygen and reduces their ability to absorb and carry oxygen throughout the body. Continuous exposure to relatively low concentrations of carbon monoxide can produce a wide range of disorders, such as drowsiness, nausea, muscular spasms, internal bleeding, or ringing in the ears. 30 parts of carbon monoxide per million parts of air is considered to be the maximum safe level. Busy city streets often contain 100 parts per million. So far, we have been examining the effects of air pollution on our natural environment. Air pollutants attack man-made products as well. Where large amounts of sulfur-bearing coal and oil are burned, sulfur oxides are released into the atmosphere. These sulfur oxides attack even our hardest metals, such as steel, thereby causing an increase in the corrosion rate. Sulfur oxides attack statuary and buildings. In some cities, works of art will have to be moved indoors if they are to be preserved. We now have a basic idea of how combustion pollutes the atmosphere. We may also begin to understand that within limits, the environment has systems to cleanse itself of pollutants. Plants help clean the air by taking the carbon dioxide present in the atmosphere and converting it to oxygen. The wind circulating air through the leaves and branches carries small particles of dust present in the atmosphere into contact with the plant. The plant holds many of these, thus acting as a filter to purify the air we breathe. The winds also help disperse pollutants. Many of the heavier materials settle to the ground. Moisture in the air condenses around particles such as dust and salt crystals in the air, and every time it rains, some of these pollutants are carried to the ground. Nature does have ways of cleaning the air if the pollution level does not become too great. What happens when the winds stop blowing? Most of the cleansing mechanisms stop. Some particles will still settle out, but the concentration of pollutants will begin to rise. In fact, what we have learned to call our best weather is becoming a warning of crisis. A clear, calm, sunny day soon becomes a smoggy, muggy, grim day. One atmospheric condition which is often present during these crises is fog. To what extent is natural fog affected by atmospheric pollutants? To demonstrate the effect of air pollution on fog, we will create an artificial fog in this chamber. By removing some of the air in this flask, we cause the remaining air to expand. This expansion cools the air, and some of the water content condenses around the small particles that are normally in the atmosphere. Since there are relatively few particles in clean air, we get only a small number of droplets. Therefore, only a light fog will form. By introducing the combustion products of a burning match into the chamber, we increase the number of particulates in the air, simulating the conditions of a polluted atmosphere. This time, when we cool the air, we get a very dense fog. Since the particulates are more numerous in the polluted air, more water droplets form, creating a dense fog. Hence, we observe polluted cities are foggier than the countryside. Clouds containing a larger number of polluted particles will have a higher number of water droplets of a smaller size than their unpolluted counterparts. This does not necessarily mean there will be more rain. It may, in fact, inhibit rainfall. More smog, more fog, more clouds. All of these could alter the amount of heat energy the Earth receives from the sun. This could lead to changing weather patterns on a global scale. At the altitude the jets fly, the environment is one of low pressure, low temperature, and low water vapor. Very few suspended carbon particles are normally found in this realm. When water vapor and suspended particles are introduced to the extreme cold of the stratosphere, a jet trail is formed. The jet places foreign elements into this environment: water vapor, carbon particles, carbon dioxide, carbon monoxide, and nitrous oxide. Jet trails, like clouds, are made up of huge numbers of tiny droplets, or ice crystals, as many as several thousand droplets in a space the size of a sugar cube. If the air temperature is high enough, the water droplets will not freeze. They usually soon evaporate and become water vapor again. But if the temperatures are low enough for the water droplets to freeze, the ice crystals that form take a long time to evaporate. The winds spread the ice crystals into cirrus clouds. The atmosphere does have some water vapor at 30,000 feet, and cirrus clouds do form naturally on the limited number of suspended particles found at that altitude. But in introducing millions of gallons of additional water vapor and tons of suspended particles, we are changing the natural water balance of this level of the atmosphere. Our man-made jet trails spread out into thousands of square miles of cloud cover. Measurements of cloud cover over heavily traveled jet routes show that there has been a marked increase in the number of cloudy days. The amount of cirrus cloud cover in the area between Chicago and New York has increased as the amount of jet traffic has increased. The same increase of cloud cover corresponding to increased jet travel has also been recorded between New York and London. The polar route is becoming a corridor of increasingly heavy jet traffic. Supersonic jets will fly this route at altitudes of 60,000 feet. Very little water vapor exists, very few suspended particles are found, and very few clouds are formed at 60,000 feet. Large amounts of water and suspended particles added to the upper atmosphere could result in heavy cloud layers being formed in the stratosphere above the polar ice cap. These clouds can act as an umbrella and shade the Earth from the sun, lowering its temperature. The Earth soaks up heat from the sun and radiates this heat back to space. The same cloud cover that shaded the Earth can re-radiate some of the Earth's radiant heat back to the ground, causing the temperature to rise. This change of surface temperature could alter the amount of Arctic ice, since in the Arctic the overall effect would be to hold heat in during the long winter. Jet trails are changing the Earth's radiative balance. The net effect upon the temperature of the Earth in the future is not known. At 60,000 feet, the temperature is minus 60 degrees centigrade. The ice crystals last a long time, and the water vapor and suspended particles accumulate day after day, month after month. At 30,000 feet, some of the ice crystals of the jet trail may fall to the Earth. In their passage, they may pass through clouds of water droplets that are below the freezing point, but have not yet started to freeze. The presence of the ice crystals can cause the supercooled droplets to freeze on contact as additional vapor condenses on the ice crystals. These ice crystals fall to the Earth as snow or rain. The jet trails not only have the power to warm or cool us, they also can cause rain to fall where it is not wanted, and not to fall where it's needed. The shading effect and the blanket effect, keeping heat in, are only two processes that may affect climate. There are many other mechanisms that contribute to this overall control. Scientists know that changes have occurred in our climate due to natural causes, and that man is now affecting the atmosphere to a degree which may also affect climate and induce changes. Unfortunately, we do not understand what the consequences of all of our actions will be. There is evidence that rainfall is becoming increasingly acid due to sulfur dioxide in the atmosphere. Carbon dioxide levels are also increasing in the atmosphere. Carbon dioxide has an important effect in absorbing radiation from the Earth, warming the Earth. Particulates in the air affect the radiation balance. Nitrous oxide produced by jets may decrease the amount of ozone in the upper atmosphere, Ozone screens the portion of the sunlight spectrum that is known to produce skin cancer. Ozone also plays an important role in determining the temperature distribution in the atmosphere. Each day, we are confronted with new theories or rumors about changes in our atmosphere. In this film, we have presented some facts relating to the basic mechanisms of these changes. The combustion of fuel, the effects of combustion products, droplet formation, the effects of fog, clouds, and jet trails upon rainfall and surface temperature. We study the past to keep from repeating it.